Yes, class, am I audible to all of you? Austin, Faiza, Fia, Humam, Tarif, Shahid. Others? Tarif, Shahid?
Yes, ma'am.
Okay,
Yes, ma'am.
okay. All right. See, in the last class, what we have studied, we had started with motional EMF. So motional EMF was what? Before that, we did Lenz's law. Now, Lenz's law simply tells you that the direction of induced current is in the opposite direction to the cause that is producing itself. So the cause is the change in flux, right? So that is helping in giving the direction of flux. Second, we have motional EMF. Now, EMF induced across the ends of conductor due to its motion in a magnetic field. This is called motional EMF. Motional EMF means your conductor is moving, so motion is occurring because your conductor is moving. And the conductor is moving with a certain velocity. So this EMF now that is generated in your circuit, we call it as motional EMF. So we did this small derivation, and after that we had the conclusion that E is equal to BLV. E is the motional EMF, B is the magnetic field, L is the length of conductor, V is the velocity of conductor. All right. Now look, some small formulas that are just present to help with the answers. See, if we have EMF as BLV, so see, current is voltage divided by resistance. So this becomes BLV divided by R, right? And similarly, remember we did force on a current carrying conductor BIL. So if it is BIL, can we put the value of current? This value of current, this becomes B. What is I now? I is BLV by R. So this becomes B square and this L also, no? B I L. So B square L square V divided by R. R is your resistance. V is the velocity. Power is equal to force into velocity. So force is what? Force is B square L square V divided by R. This is the force. So multiplied to velocity, this becomes B square L square V square divided by R. Fine. So power, this is what? This is the formula of power. Power, this is force and this is current. This you should remember. Note down this, then we'll practice one question from this. Yes, Austin. Yes, yes. Earth magnetism. I was also checking about the same because last year it was again added, and I think this year it is again deleted. Last year it was deleted. Last year it got added. So I think it is once more. I'll also confirm, but most probably Earth magnetism. Yes, this is deleted. Right. I'll just confirm in the next class. Also. Tomorrow I'll confirm. Others also, if you please have confirmation, do share it with me. Also, class, please share your date sheets on the WhatsApp group. Half yearly's date sheet you must be having. Please share it on the group. And yes, all those who have written, what's the answer? You have to tell me the value of EMF. It's a very easy question. Fia, you're still not added on the group. Anyone else apart from Fia? Okay, I'll get you added right now. Wait, Fia. In the previous class, Fia, I had asked you to text me also, no? Because I do not have the numbers saved, right? So it's difficult for me to find out. In any ways, let me get you added also on the group, but do text me. Pia, please check. Have you received the table? See, an aircraft with the wingspan, somebody has answered. No, Shahid has answered. Okay, Shahid. Anyone else? Only Shahid has got this question correctly. This was a very straightforward question. You have the speed with you. Now, you cannot use the speed like this. Speed is 10800 kilometer per hour. 75.6 into 10 to the power minus 5 volt, Fia. And 4.2 into 10 to the power minus 2 volt, Shahid. Now see, to convert this into meter per second, we multiplied by 5 by 18. Fia, did you multiply this? This becomes 5400 by 18.
Ma'am, I converted 40 meter into kilometer, ma'am.
You've converted this into meter per second? Or you have converted 40 meter?
No. Yeah, that to kilometer I converted.
No. See, 40 meter, this is the length. 40 meter is fine. Oh, you have converted this into kilometers.
Yes, ma'am.
No, see, then you have to convert this also. When this is given in SI unit, this is given in SI unit, you only have to change this and make this into SI unit. Got it?
Okay, ma'am.
This should be around 100 meter per second. And what is the magnetic field given? All the units should be same. You have to keep in mind the SI unit of magnetic field also, no? So 1.75 into 10 to the power minus 5. So here we have BLV. This is equal to 1.75 into 10 to the power minus 5. 40 into 300. Okay. Now see, has anyone solved this? Shahid, you did the same steps? I do not
No.
remember the answer. Same steps, no? Please, someone else also just cross-check once so that we are not writing the incorrect answer. This is the answer. This has to be solved. Just check once. Someone please confirm. Shahid has answered this. I do not remember this answer. Just please someone calculate and confirm. 2100. Shahid, 2100 volt.
Yes, sir.
Yes, ma'am, it is 2100 into 10 raised to minus 5.
Into 10 raised to power minus 5. This, no?
Yes, ma'am.
Okay. Shahid, please check your calculations once. You got 2.1 into 10 to the power minus 1. Okay. So that's correct. Earlier you had written something else. That 0.21 volt only, which Humam is also answering. Fine. Good. See, class, now you have the concept of eddy currents. This is also not included in your CBSE syllabus now. It has been deleted. But still, let us just quickly revise it briefly. We'll do. Eddy currents are eddies means whirlpools. So eddy current means suppose you are having a block. So current flows in this manner, like the whirlpools, like this. Or if it is in a circular form, in spiral form, like this. This is the way a current flows. So these types of currents which are produced on very thin, these are very, very thin sheets, very thin sheets. All right, these are whirlpools. We also call them as Foucault current. This is enough for you to remember. Nobody is going to ask you this in your
Okay.
exam. Just remember the application of it. It is used in induction furnace, electromagnetic damping, electrical brakes, and speedometers. See, speedometers, all of you know. Speedometers are what devices? They measure the speed of the particular vehicle. Then electric brakes. Electric brakes are what? Brakes are your vehicle stops by them, but eddy currents are produced within them. Yes, Shavez. See, Shavez. Basically, eddy currents are these currents. Not otherwise, if when you have a normal current, your general current, this travels straight like this within the wire. It travels straight. How? Why electrons are moving like this in a straight fashion. This occurs usually. In case of eddy currents, the currents travel in a whirlpool like this. Or if it's a square plate, then like this. So it is used, we call these types of current as eddy currents because eddies means only whirlpools. This is also called as Foucault current. So application is that it is used in speedometers. This I have told you in vehicles. Electric brakes are mainly the brakes that are applied in your circuit, which are connected through circuits. If the circuit breaks, electrical brakes will not be applied. Then you have the concept of electromagnetic damping. See, electromagnetic damping force is proportional to the induced current that is produced. And the strength of the magnetic field which is produced, the speed with which it is moving. Already that is what is meant by electromagnetic damping. And ultimately, slowly what happens? This decreases. The value of damping decreases. All right. That is what is meant by it. It's like a dissipative force, you can say. It's like a dissipative force. Then induction furnaces are what? They are basically just like batteries. They are present, made up of different types of materials: steel, copper, aluminium, some alloys, and they have a particular range. Induction furnace, so they are present within the cell. Now heat is applied by the induction of heating material, whichever heating material is used. That is what is meant by induction furnace. All right. Electromagnetic induction, you have medium frequency electric furnaces, different, these are present. So this is about eddy currents. Now we are left with induction. Eddy currents, I'm again telling you, this has been deleted. This part, no need to learn it for your exam, but this is very important for you to know as for your knowledge, because eddy currents term will come again also, not for in your class 12, maybe in your higher studies. Eddy current is a very common term which you should be aware of. That's why I'm discussing it. So note it down, class. And one more thing, see, now the timings of prayers have shifted earlier, so I have to take a 5 minutes break also, then I'll join back. By the time, just complete this, and then we'll have a 5 minutes break, then we can continue. Class, the screen is sharing with you.
Yes.
It's no? Okay. So yes, what we were discussing, eddy currents we discussed. So eddy currents, this is just for your knowledge part. This won't be included anywhere. Now see next, let's start with the next topic then. Induction. See, induction, this is all very similar to what you've studied. This is very similar to Lenz's law also. This consists of magnetic flux also. So all the topics which we have studied in EMI till now, that will be connected in here. Now, induction are of two types. One is self-induction, other is mutual induction. So first, let us just focus on self-induction only. All right. Let's focus on self-induction only so that then we'll focus on mutual induction. Now, what is meant by self-induction? Self-induction means, suppose I have a coil. Fine, this is a coil that I have. Certain current is flowing in certain direction. Let's say this is flowing anti-clockwise. Fine. Now, suppose, let's say the magnetic field in which this coil is present. This is just a coil. This is magnetic field is present. This magnetic field starts increasing. A coil was present, current carrying coil, carrying current in the anti-clockwise direction. Yes. Now, this is the magnetic field starts increasing. All right, the magnetic field then starts increasing. Now, when the magnetic field starts increasing, which quantity will increase? Magnetic flux, because magnetic flux is basically number of field lines that are flowing per unit area, right? So if magnetic field lines are increasing, it means your flux within the coil is also increasing. Now flux within the coil is also increasing. Current is flowing within this. Now see, when the flux increases, what we have studied, there is an induced EMF generated. Yes, because of change in flux. Flux is changing from a certain value. Flux has increased now. So this is a change. Let's say initially it was 5 Webers. Now after increment of magnetic field lines, this becomes 15 Webers. So there is a change in flux. So whenever there is a change in flux in your system, an EMF will be generated. So within this same coil itself, C class, now within the same coil, EMF is also generated. Fine. What happened? Magnetic field increased, magnetic flux increased, so there's an EMF generated. So magnetic field changed within the same coil, magnetic flux increased within the same coil, EMF is also generated within that coil. So this phenomena is what we call as self-induction. Induction is you are inducing something. Remember in the first classes of electrostatics, we have studied regarding induction. I told you induction will come. You have a separate lesson on an electromagnetic induction. It was temporary electrification. We just took a glass rod and we brought it near the neutral content and all the charges separated. Remember we did induction. So that was the phenomenon of inducing something. You were inducing the charges. You are separating the charge by some induced device, right? That is what is meant by self-induction. Now, why this is what is meant by induction? You are inducing something. There was no EMF present, but you intentionally increase the EMF, increase the magnetic field so that flux increases, and when flux will increase, EMF will automatically be present, induced EMF will be present according to Faraday's laws of EMI, right? That's why we have studied Faraday's laws of EMI earlier only. So, and why self? Because this is occurring in the same coil. The coil is itself increasing the magnetic field. The coil is itself increasing EMF for itself. That's why we call this as, this is now self-induced EMF. This EMF that we get, this is self-induced EMF. Now class, in some books you will find one more term for this. Back EMF. One term for this is back EMF. All right, this is what is meant. So self-induction is a phenomena of production of induced EMF in a coil when changing current passes through it. Changing current produces changing magnetic field. Changing magnetic field produces changing magnetic flux. Changing magnetic flux induces EMF, and the entire process is called self-induction. See one example. Let's see. Then you can write down all these points. See, suppose in this, current is increasing. The value of current from 0, it is increasing, and it is reaching a very highest value, let's say I max. Current has increased. So flux will also increase. Current has increased, flux will also increase. This will produce EMF. Now the EMF that will be produced in the circuit, this will be induced EMF or back EMF. Fine. This is a coil. This is a coil. Suppose, so see, why current increase in this? Because you are closing a circuit. Earlier circuit was open, no current was there, so current was 0 initially. When you started closing the key, gradually charges started releasing from the battery. Charges started releasing from the battery, you have lots of current increasing. When current increases, then there's a change in magnetic flux which produces EMF. Now when we are opening a switch, when the switch was closed, current was at its maximum value. Now when you are opening the switch, now what is happening? Current is coming back to the battery. So if the initial value of current was 5 amperes right now when you have opened the switch is off. Slowly from 5 amperes, it will become 4.9, 4.8, 4.7, till it decrease till 0. So here what is happening? Current is decreasing, flux is decreasing, again changing flux. So EMF will be produced in the circuit. That's all what you have to remember in the theory part of self-induction. Rest of it is just formula and numerical that I'll discuss. First note it down.
I just do the
Now see, let us come to the calculation part class. All of you have completed. See class. Here now what is happening? When the current is increasing, flux was increasing. Current decreased, flux decreased. If current increases by 3 units, flux will increase by 3 units. If current decreases by 4 units, flux will decrease by 4 units. So at the last, what is happening? Phi is directly proportional to current. The magnetic flux is directly proportional to the current. Here we get a constant, that is Li. This is our formula. What is phi? Phi is the magnetic flux. I is the current in the coil. And L is what? Coefficient of self-induction. This is coefficient of cell induction, or we also use the term self-inductance. Self-inductance will be used a lot in AC, alternating current. Self-inductance. Fine. So how can you define L also? If we take current as 1 ampere, so flux and L will be same. It means coefficient of self-induction is the amount of magnetic flux for 1 unit of current. That's it. One more formula of EMF we did, that was E is equal to minus d phi over dt. Phi is equal to Li. Right now I've told you. So this becomes d Li, means the value of phi over dt. See, L is a constant, so that becomes minus L di over dt. So what's the formula? EMF is minus L rate of change of current dL over dt. This is rate of change of current, rate of change of current. Fine. So self-inductance is numerically equal to the magnetic flux when unit current flows through it in 1 second. So SI unit will be what? See, this is 1 EMF, that is 1 volt, divided by di over dt, that is 1 ampere by 1 second. So we do not write all this stuff. Voltage, voltage seconds per ampere. This we do not write. We have one proper unit, that is, this is equal to 1 Henry. H will be used, Henry, for self-inductance. So self-inductance is numerically equal to the magnetic flux when a unit current flows through it in 1 second. This is the above part only. And dimensions also, see, L is equal to phi divided by I. And flux is BA also, BA cos theta. So the dimensions, no, MLT. MLT and A. M square L to the power minus 2, A to the no, T to the power minus 2 and A to the power minus 2. This is L to the power 2, T to the power minus 2, A to the power minus 2. This is from your class 11th. Nobody is going to ask you the dimensions, but you should have written it and just know how, if by chance dimensions are asked, because these are helpful in the calculation part. Solenoid we'll see later. First note down this formula part and all these points. So phi is equal to Li. This formula all of you should remember. And there is no derivation in this. Direct. They are proportional, so they are proportional. See class, self-inductance of a long solenoid. This is just a small derivation that comes. So remember this. What is the magnetic field of solenoid? This is B is equal to mu naught Ni. And N was what? N was number of turns per unit length. This is not just the number of turns, right? Flux is what? Flux is Ba. So let's put the value of V. So flux becomes mu naught I A. Mu naught Ni. So N, let's write this. This is Ni, right? Mu naught Ni. B. This is magnetic field and area. All right. Now see, magnetic flux linked with the entire solenoid. This means flux linked with each turn multiplied to number of turns. What are the number of turns? This is number of turns per unit length. This is length. This is number of turns. So number of turns is equal to N into L. Yes, this is the number of turns. So flux linked with each turn. This is mu naught Nia. And what is each turn? Number of turns, N into L. N into L. So flux phi becomes mu naught N square I A L. Yes, mu naught N square I A L. Yes. Now phi is equal to Li. So let's equate both of these. See class, this equation and this equation both are same ultimately. You can equate both of them, equate 1 and 2. So you have Li equal to mu naught N square I A L. LL will be cancelled. Oh no, this is length. No, this will not be cancelled. Current will be cancelled. One is length. Area is current is cancelled. So we have the value of L with us. L is equal to mu naught N square. This is the value of self-inductance. Fine, this is the value of self-inductance that we'll be using. Now N you can put also N will be equal to mu naught N square by L square into it. Let me make this as small L, otherwise this is becoming confusing. Even I cancelled it. Let's make this as L. So that there's small L is length and capital L is self-inductance. Please be careful with this class, the symbols, because no, otherwise like I did, you all will also cancel L. This is one is self-inductance, this is current. Okay, so this is the formula mu naught N square A, and this is the formula if you have to write it in terms of number of turns per unit.
Ma'am, it is mu naught N square A L, right, ma'am?
Mu naught N square A, yes.
L also should come, right?
Hmm?
L. Length should also come.
Yes, Fia, length is there. Fia, what's your question? Length is there, number of turns are there.
No, ma'am, L is equal to mu naught N square A L, right?
L is equal to mu naught N square A. What should come?
L should not come.
Okay, this you're saying.
Because,
This length.
yeah,
This
yes,
length
ma'am.
you're saying.
Yeah.
Okay, okay, yes, yes. See, when we talk about this length, you know, this length will also come. This length will also be there. L. This you're saying, no? So when you're writing here, you can delete it from the denominator. Because 1L will be cancelled. N square L it will remain. Yes, I missed this small L. Thank you, Fia. Small L was also there, no? Actually, see, that's what I'm telling you. The small n and capital L, because both the symbols are same, it becomes confusing, and it is becoming confusing for me as well. So please be careful with the symbols. Otherwise, self-inductance and length, this will become very confusing for you. So we have length in the formula, and we are calculating it for self-inductance. All right. Note this down.